All right, here we are, lecture 14b. Okay, so here we're going to work a problem, and it's kind of an unusual problem. I like it because it kind of gets at some angles and some things and makes us think a little bit about the signs in this problem, because it's definitely very important that we get into that. Okay, so, and also we're going to have to use some of our tools, which is always really great. Okay, so what we've got here, and this is interesting. So this here right here is the plan view. Okay, so for those of you who are unfamiliar with the plan view, what that means is that you're looking straight down on something. Okay, and this right here is the side view of the same thing, side view. And what we've got is we've got some kind of weird cart, and the cart is moving to the right at 3 meters per second. Okay, and what's happening is we've got some water flowing in from the left, QA, and it's flowing in, and the cart has this like splitter on top of it, and basically what's happening is as the water comes in, some of it is going off that way, and some of it is going down to the bottom. Okay, as you can imagine, this is exerting a force on the cart, or on the, in this case, I guess the water's exerting a force on what we're going to call the vane. Okay, because it's just the thing that's redirecting the water, so that's probably what's causing it to move forward. Okay, there's some other forces. Probably if we were to work on the whole cart, there would be other ways that we could drive at this. But in this case, what they want to know is they want to know what is the force of water on the vane. Okay, so I'm going to call that WOV. Okay, and sometimes this is not the same thing as force VOW, which is the force of the vane on the water. Okay, so you'll see me kind of switch those letters up as we go into these problems, because it's important to identify what it is you're working with. Okay, so what I'm going to do here is, the first thing I want to do is let's identify our tools real quick. All right, so here's our set of tools. Okay, and probably what I'm going to do at some point in time is I'm going to go ahead and duplicate these, because we're going to need them again. Okay, so let's just put them over here somewhere. Okay, because these guys show up a lot. Okay, but in the meantime, okay, we don't have a manometer in this problem, so there's not going to be any manometers going on. There's always geometry to deal with, but in this case, based on this plan view and this side view, there's no elevation changes in any of this, so really this is going to take a back seat. Okay, there's no z's. Okay, based on, I forgot to give you guys one thing. Okay, VA equals 20 meters per second. Okay, so anyway, so what are we going to deal with here first? And one of the things that comes up here is, when do you need to know momentum equation? When is that going to come up? And I'm going to tell you right now, it's whenever you want to know forces. Okay, so if you want to know forces, okay, on a fluid, you're going to need the momentum equation. There's really, a moving fluid. Okay, so if it's a static fluid, you can just use hydrostatics. But if it's a moving fluid, you're going to need to use this momentum equation. So let's talk about the momentum equation, and then see if we need continuity or Bernoulli. Okay, so let's do the x direction momentum equation. Okay, so the x direction momentum equation. Okay, so here is our x direction momentum equation. Okay, and so we've got some forces we'll have to deal with, obviously, on the fluid. So, we need a control volume, right? So let's draw a control volume. And the control volume here is very important, and especially like whether or not you're dealing with the walls as well. Okay, and so what I'm going to do right here is I am just doing a control volume of the fluid. Okay, I'm not interested in the walls of this thing. Okay, so it's just the fluid itself. Okay, but what's key here is I'm going to need Vx and I'm going to need Q for my ends. Okay, where are my ends? Well, this is an in right here. Okay, that's my only in. And in the x direction, this is my only out. Okay, this one is not carrying, this one down here is not carrying x momentum. Okay, so we're not worried about that one at the moment. Okay, but that means I need V's and I need Q's. Okay, so let's go ahead and see if we can't drive at that. Okay, so we're going to use a little bit of continuity here before we get into this. So I'm going to do an aside over here. An aside. Okay, and my aside here is going to be continuity. There's an I in there, continuity. Okay, so here we go. So we've got QA. So in row QA equals out row QB. So let's say row QB. Okay, plus out, which is going to be row QC. Okay, there's no signs on those, like doesn't matter what angle they are because that's just mass. Okay, noting that same density of all of these. So QA equals QB plus QC. But we know from the givens that QB equals half of QA. So that means that QC equals QA over 2. Okay, so now we know QA and QB are both half of QA. Okay, so now we have to figure out what is QA. Well, we've got this number right here, and we've got a diameter, right? So we can get at that. So we can say that QA equals, sorry, don't want to get too far ahead of myself. Okay, I get excited. VA times the area of A. So QA equals 20 meters per second times the area of A, which is pi times 0.1 meters squared over 4. So QA equals 0.1335 meters per second. And I really should, cubic meters per second. And I really should have another significant figure on there. But whenever I worked this, I didn't have that. Okay, so then that means QB and QC are each a half of that. Okay, so that's going to be 0.0668 cubic meters per second. Okay, so that takes care of in our momentum equation. Let's get rid of these little squiggles here. That means that now, as I work through this, I've got my Q's, okay, for really every direction. But now I need velocities, right? And so I have the velocity going in is given at 20. But what's the velocity over here? Okay, at B and at C. Well, we don't know. Is there any way to get at it, right? I know the Q, okay, because I just solved for that. But the only way to know the velocities would be if we knew these diameters, right? This diameter, if I knew the diameter and I knew Q, I could get it. But that's not given. Okay, any thoughts? Okay, take a moment and think about it. Because this one shows up kind of rarely on a test, but it does confuse my students. So the way we're going to do that, I've already used continuity, is we're going to use Bernoulli. Okay, and so I'm going to pick a point like right here. This is point 1. And this is, well, this is point A, let's call it. And this will be point B. And what I'm going to do is, here's my streamline. I'm going to assume the flow is inviscid. It's incompressible because it's water, and it's got a lot of other, I can't remember all of the assumptions off the top of my head, but, it's not really inviscid, right? But we're going to assume that it is. And basically, we can use Bernoulli. So here's my second aside, will be Bernoulli. Bernoulli. Okay. Oh, and those assumptions were, is it steady? Yes, it's steady in this case. Is it inviscid? No, it's not inviscid, but we're going to assume it is. Is it compressible? Yes, because this is water. And then are these 2 points along a streamline? So we'll say yes. Okay, so I'm going to go the pressure at A over gamma plus ZA plus VA squared on 2G equals PB on gamma plus ZB plus VB squared on 2G. Now, I would like to run through this really quickly because I've done Bernoulli 10 million times. However, you have not. So let's go ahead and do this proper. Okay, what's the pressure at A? Anybody? Okay, well, notice A is in the atmosphere. Okay, it is where the water is entering. Okay, if you go a little bit further in from A, there will be pressure there. But right here, there's no pressure. So we'll go with a 0 right there because we're going to call it gauge. Okay, the same thing's going to happen at B, so we're going to make that 0. Okay, what about the elevation? Well, whatever A is, B also is. So that's going to be 0. And ZB is also going to be 0. So what that tells us is that VA squared on 2G equals VB squared on 2G, which tells us that VA equals VB. Well, that's cool. But I could do this again for C, and I could just use a different streamline, and I would get the same thing. So VA equals VB equals VC. That's pretty cool. Okay, now what is that number, though? Okay, there's a temptation to say that it's 20, but it is not 20. What is it? Well, we have to remember the cart is moving at 3 meters per second. Okay, our control volume is moving at 3 meters per second. But this fluid is moving at 20 meters per second relative to the Earth, and it's actually only coming in here at 17 meters per second. Okay? So, we can go up over here. Oh, wait. So this is... And actually, I made the mistake a second ago, didn't I? This should have been, my apologies, this should have been 17 meters per second. Okay, this should be 17. Okay, for that exact same reason. Okay, so it's 20 minus 3. Okay, however, these numbers are correct. Okay, I worked them out with 17. All right, so now that we have all this stuff, okay, we can come down here, and now I know all of my velocities. Okay, and we're going to get at the forces. Okay, so what are the forces on this control volume? Okay, so again, we're looking at this thing in green, okay, which I have now drawn all over, but we're just looking at this green thing. Well, what forces do we have on it? Okay, when identifying forces, I like to think in a few different ways. I like to think about, okay, body forces. We've got gravity, right? So here's our control volume. It's kind of easier to draw down here. Okay, we've got gravity. So we've got the weight of the water coming downwards, right? We've got a normal force from the vane pushing back up. We've got force normal. So in the z direction, it's pretty easy. So that would be the z direction, and this will be the x direction, and this will be the x direction, and this will be the y direction. And but what about in the x and the y? Okay, well, hopefully you see that there's a few different forces here. One potential one is the pressure, right? So there's pressure acting on these openings, right? It just so happens that what are those pressures? Well, there's 0, right? Well, they're not technically 0, they're atmospheric, right? So we're going to make them gauge. Okay, so those pressures go away, so we don't have to worry about them. Okay, we're going to go ahead and include it in the x direction just so I can show you how to deal with pressure because it's going to happen. So we're going to spread this term out. So I've got PA, AA, so that's the force of pressure on A, and that's in the positive x direction. Okay, now on location B, okay, that looks like that one's going to be negative, and that's going to be PB, AB. Okay, now not all of that is in the x direction, right? So we're going to say cosine, well, I guess in this case it's really the sine of 45, isn't it? It is the sine of 45. Doesn't matter because it's 45. So sine of 45. It doesn't matter what you would, in this case, just because it's 45 degrees. But if it were a different angle, it would really matter. Okay. What other forces do we have? Well, basically we have this force of the vane on water plus the force of the vane on the water, okay, in the x direction. Force Vaux. Okay, anyway, force Vaux. Okay, now what is that force? Okay, well, it's a few things, right? It's basically a reaction because the water comes in pretty fast and then it kind of hits over here somewhere. And so that causes kind of like a normal force or reaction. Okay, that's going to kind of like push back on the water. But it's also all of this, all of this viscosity or all the friction along the sides of these walls. Okay, so it's going to be all of that. Okay, and some of that will be in the x direction and some of that will be in the y direction. Okay, so it's all of that kind of combined into one force. It doesn't split them apart. It just calls them all one force. It's basically the effect of the vane on the water in the x direction. Okay, now let's deal with these momentum terms. Well, in the x direction, we've only got one term. And so that's going to be, let's see here, V, A, okay, rho of water in this case, and Q. So that's going to be QA. Okay, so that takes care of what's happening at A. equals, okay, what do we have that's leaving in the x direction? Well, we just have what's going on at B. So that's going to be VB. Okay, in this case, it looks like it's going to be sine of 45 degrees. Okay, so this is the x momentum. Okay, times the rho at B, which is just rho because it's not changing, QB. Okay, what's nice about this equation when it comes out is that there's no pressure. Okay, so these pressure terms are just going to go away, but I included them just for completeness here. Okay, so this one's going to go away, this one's going to go away because there's no pressure, because it's just gauge pressure. Okay, so FVOWX plus, let's see here, this is what, 17 meters per second times the rho. What's the density of water in the SI system? It's 1,000. Okay, kilograms per cubic meter. Okay, times QA. Well, what's QA? Well, it's 0.1335 cubic meters per second. Okay, so note the units here, cubic meters are going to cancel, and we get kilograms meters per second squared. A kilogram meter per second squared is a Newton, okay, which is good because we're trying to solve for forces here. Okay, equals VB. Well, VB is 17 meters per second. Okay, the sine of 45 degrees. Okay, rho again is 1,000 kilograms per cubic meter. And QB is 0.0668 cubic meters per second. Okay, again, notice these cubic meters are going to cancel, and we're going to get kilograms meters per second squared. So we're going to get newtons, which is exactly what we want. So if we solve this, we're going to end up with, it looks like we're going to end up with a negative number. Force Vaux, okay, equals negative 1467 newtons. Okay. Oh, I should have said, by the way, I was assuming when I never drew it on my free body diagram up here. Well, I never drew my free body diagram. Well, that's a colossal mess. Okay. Well, I'll draw the free body diagram now, but I should have drawn it a long time ago. Here's my free body diagram. Okay, now I want to note this is of the water. Okay, we've got pressures, but the pressures aren't really going to come into it, but we'll go ahead and draw them on here. Okay, I've got a force vane on water in the X. I've got a force vane on water in the Y. Okay, and then I've got all these pressures. Okay, so it's going to be PBAB. This will be PAAA, and this will be PCAC. Okay. Anyway, so all right. So that means that this force of the vane on the water is actually in the negative direction. Now, does that make sense to you? Now, it should, because this water is coming in, and if there were no forces on it, like if we look at this picture of it right up here, okay, let me draw with a nice thick line. Okay, let's make it kind of bluish. Okay, so as this water is coming in, note that it would just keep on going, right? But some of it goes this way, right? And some of it goes this way. It loses x momentum, right? It's not going forward at 20 meters per second relative to the Earth anymore, or 17 relative to the vane. It's going at 17 off at an angle, and it's going this way, which has no x momentum at all. Okay, so something has caused it to lose that x momentum. To do that, you need to push back on it in the negative direction. Okay, so that is why. So that force, okay, I kind of knew it was going to be in that direction, and you should have too. But, you know, the nice thing is you don't have to know, right? You can just let the math figure it out for you. Okay, so let's do the y direction now. Okay, y direction. Okay, this is going to be very similar. And we're going to say the sum of the forces in the y direction. Okay, plus the sum in of Vy rho Q equals the sum out of Vy rho Q. Okay? So this will be a little bit better since I've managed to draw this a little bit simpler, since I actually have a free body diagram. This is why we do free body diagrams. They make your analysis much easier. Okay, instead of guessing kind of like I was earlier, we can just look at them. Okay, so in the y direction, so here's y direction, here's the x direction. In the y direction, what forces do we have? Well, we've got F vane on water in the y direction. Can you guess which way that is? Okay, is it pushing the water up net or is it pushing it down net? Obviously, some of it is pushing up and to the right, and some of it's pushing only down. So which one of those is more important? Okay, I have a theory that this is going to be more negative than positive, only because the water that turned that way is going 100% down, whereas this stuff is not going entirely up. Okay, so that's my guess. Okay, but obviously, if this were split symmetrically, the force of the water, the vane on the water, would be 0. Okay, in the y direction. All right, so plus. Okay, so let's see in the y direction. In, do we have any flow in? We don't have any flow in, right? So I usually like to draw those like this. Okay, so here's my flows. Okay, and I draw them across. Okay, so those are momentum fluxes. Okay, so this is VA, this is VB, this is VC. Notice VA is the only one that's in and it doesn't have a Y component. VB is out. Okay, so I'm going to just put a 0 right here. So let's start with the VB. Okay, VB, okay, times the cosine of that theta, which is 45. Okay, so that's this angle right here is 45 degrees. Okay, now we need rho at B times QB. Okay, now we have to do VC. Okay, notice VC is plus negative VC. Why is it negative? Oh, because in the y direction, it's got a negative value. Okay, it doesn't have a cosine, but that's its directionality, right? It's downwards. Okay, now we'll do rho, and we'll do QC. Okay, so that should set us up pretty easily, or pretty well, for F Vowie equals the VB, which is going to be 17 meters per second. Okay, cosine of 45. Rho, again, is 1,000 kilograms per cubic meter. Okay, and QB, what was QB? 0.0668, I believe. 0.0668 cubic meters per second. Okay, the cubic meters are going to cancel. Get kilograms, meters per second squared. What we're looking for. And something just glitched on my computer. Okay, so then we'll do minus or plus a negative 17 meters per second. Okay, times 1,000 kilograms per cubic meter times QC, which is 0.0668 cubic meters per second. Again, the cubic meters are going to cancel, and I'm going to get kilograms meters per second squared. A kilogram meter per second squared is, in fact, a Newton. So F Vowie equals negative 333 newtons. Okay, so in fact, it is in the negative direction because I assumed it was upwards. Okay, so what about the Z direction? The Z direction. Okay, well, we've got forces in the Z direction, right? I kind of drew it over here. Normal force equals the weight. But from a momentum standpoint, nothing's really going on here. So we're not even going to worry about that. Okay. We could solve for the normal force here, or this, and it would just be the normal force minus the weight. Most importantly, on most problems, you need to account for the weight as one of your forces that goes into your sum of forces. Okay, but not on this problem. We're not going to worry about the Z direction. Okay, so don't worry about this for this problem. Okay. If you wanted to, you could include the F normal if you wanted to there. Anyway, so F, to kind of wrap this one up, F vow equals, okay, if I want the magnitude of that sucker, okay, it's going to be, let's see here, the square root of, what was that first number? 1467. 1467 newtons squared plus 333 newtons squared at an angle at inverse tangent. Well, let's see here, at theta equals inverse tangent of the, let's see here, of negative 333 newtons divided by negative 1467 newtons. Okay, so all right, so following the math, we end up with 1500 newtons at an angle of 12.8 degrees. Okay, noticing that because these are both negative, it's kind of one of these 12.8s. Okay, so it's back and as to the left and down. Okay, so basically you've got fluid coming in like this, and then it hits a force that's going like this. And because of that force, this flow splits like this and like that. Okay, kind of makes sense to me. All right, are we done? Let's see here, what were we looking for? Required, force the water on the vane. Oh, we're not done. We want the force of the water on the vane. All right, so here's how we do that. The force of the water on the vane. We have the force of the vane on the water. We want the force of the water on the vane. So what law is this? This is Newton's third law. For every action, there's an equal and opposite reaction. So we're going to do it like this. Whew, that last step was a lot of work. All right, so it's going in the opposite direction. Okay, so the force of the water on the vane is 1.5 kilonewtons, 12.8 degrees north of east. All right, guys, so that is your first glimpse at the momentum equation, what I think is the hardest part of this course, but I am kind of alone on that. Oh man. Anyway, I hope I didn't just overwrite my other project. So anyway, I hope y'all are having a good day. Take care of yourselves. Please come see me if you're struggling. I'm here to help. All right, take it easy, and goodbye. So that is